Hey, Harsh here. Today we will be covering the basics of load balancing. By the end of this session, you will understand why you choose one algorithm over another and the crucial role that load balancer plays in maintaining session state in a distributed system. To truly appreciate load balancing, we must understand its primary objectives. The first is scalability. Instead of buying a massive expensive server, which is vertical scaling, we buy several commodity servers and distribute the load among them. This is horizontal scaling, which is often more cost effective and resilient. The second is high availability. The load balancer acts as a single point of entry but a multi point of exit. Its most crucial role here is health monitoring. A good load balancer doesn't just check if a server is on, it runs continuous, sophisticated checks. It might perform a simple L4 TCP handshake or a more intelligent L7 check by sending a HTTP GET request to a specific endpoint, wait for a 200 OK response. If a server fails its health check, the load balancer immediately stops sending traffic to it and gracefully reroutes those connections to the healthy server. This instantaneous failover is what ensures your application remains available 99.999% of time even when the hardware fails. Round robin is the default for a reason. It is simple and introduces almost zero processing overhead for a load balancer. It's an excellent choice for a fleet of identical servers handling entirely stateless traffic. However, modern infrastructure is rarely symmetrical. You might have legacy hardware alongside cutting edge machines. This is where weighted round robin becomes essential. With weighted round robin, you manually assign a weight value to each server representing its capacity. If server A has a weight of 3 and server B has a weight of 1, the load balance will send 3 requests to server A for every 1 request sent to server B. This ensures that powerful servers are kept busier, maximizing the utilization of your entire infrastructure. Least connections is the first algorithm that introduces state awareness into the load balancer itself. It's dynamic, meaning the distribution decision is made in real time based on current operational metrics. This is superior to round robin when you have connections of widely different durations, such as a quick API call versus a long file download. The technical challenge here is the overhead. The load balancer must constantly monitor and update the connection count for every server. To get the best of the both worlds, we use weighted least connections or WLC. This elegantly solves the heterogeneous server problem for dynamic load balancing. Instead of just picking the server with 3 connections over the server with 5, it divides the connection count by assigning weight, constantly optimizing for highest performance across the entire fleet. Now we are moving into the realm of truly intelligent load balancing. Least connections is a good proxy for server load, but it is not perfect. What if a server has very few connections, but one of those connections has triggered a massive CPU task that has slowed the entire server to a crawl? The least connections algorithm would continue sending traffic there, leading to a poor user experience. This is where least response time shines. This algorithm not only looks at the number of active connections but also actively measures the latency of each server. It does this by constantly sending small health check probes and timing how long it takes for the server to respond. When a new request arrives, it picks the server that offers the best combination of low connections and low latency. This is a much more accurate reflection of a server's real-time ability to handle new work and is a direct measure of the performance your users will experience. If you need the absolute highest degree of accuracy in your load distribution, you use a resource-based algorithm. This method goes beyond proxies and external checks. It requires installing a lightweight agent directly on each application server. This agent's only job is to constantly monitor the server's core vitals like CPU utilization, available memory, disk I/O, and stream that data back to the load balancer. The load balancer, now armed with perfect information, can send the next request to the server that is genuinely the most idle. This is the ultimate solution for preventing server overload, especially in environments with unpredictable spiky workloads. However, this power comes at the cost of complexity. You are now responsible for the life cycle of these agents. Do they start on boot? What happens if an agent fails? How do you roll out updates? This approach is incredibly powerful but is typically reserved for performance critical applications where the added operational overhead is justified. So far, we have focused on balancing the load within a single location. But what if your users are all over the world? This is where geographic load balancing, or GSLB, comes in. GSLB operates at a much higher level, typically during DNS, to route users to the data center that is physically closer to them. When a user in Tokyo requests your website, the GSLB system ensures that they get the IP address for your Tokyo data center, not the one in London. This dramatically reduces latency because it shortens the round trip time for each single packet. This is also a cornerstone for any robust disaster recovery strategy. If your entire North American data center is hit by a hurricane, the GSLB can detect that failure and automatically start resolving your domain name to the IP address of your European data center, keeping your service online for all the users. It's the key technology that allows application to have truly global, high performance and resilient footprint. IP hash is necessary evil when we cannot decouple our application logic from the state. When you need a sticky session where a user stays attached to the same server, IP hash is the simplest L4 mechanism. However, modern network topology creates severe limitations, especially with NAT and corporate proxies that can funnel thousands of users through a single IP, creating a server hotspot. For this reason, for layer 7 stateful applications, the more robust solution is cookie-based persistence. By injecting a server ID into a client cookie, session affinity is preserved reliably. The load remains balanced for users who don't need stickiness, and the massive imbalance from proxies is avoided. We all use Netflix. With over 300 million subscribers, their scale is staggering. So their load balancing strategy has to be world class. It's a beautiful multi-layered approach. First, when you open up the app in your home, say Brazil, your device does a DNS lookup. Netflix's global server load balancer, GSLB, sees that request, and rather than picking the closest data center, it uses a more advanced latency optimized system. It might determine that due to network congestion, routing you to a US East region that is momentarily faster than the geographically closer South American one. This is geographic routing evolved, and it's the first step to giving you a fast, snappy experience. Once your request hits the chosen AWS region, it doesn't go straight to a Netflix server. It hits the Amazon's own powerhouse load balancer, the Elastic Load Balancer, or ELB. The ELB handles the raw incoming flood of traffic, decrypts the HTTPS traffic, that's SSL termination, and performs the initial distribution across Netflix's own front door, which is an API gateway called Zool. Now we are inside the Netflix's ecosystem. Zool is an incredibly intelligent layer 7 software load balancer. It inspects your request and understands what you are trying to do. If the URL path is /play, it knows to route that request to the pool of microservices responsible for starting a video stream. If it's /browse, it routes you to the recommendation service. And for this internal routing, you can bet that they are using advanced dynamic algorithms like least response time or custom resource-based metrics to ensure every single one of those millions of simultaneous API calls is going to the healthiest, fastest, and most available microservice instance. This multi-layered system is a masterclass in how you combine different load balancing strategies to achieve global scale and resilience. The choice of component determines your cost, scalability, and performance ceiling. Hardware load balancers are traditional powerhouses using specialized silicon for the lowest possible latency. Software load balancers like HAProxy or Nginx run on commodity servers, making them cheap, flexible, and perfect for virtualized and containerized environment. Finally, the modern standard is cloud load balancers. These are managed services that abstract away from the infrastructure, scale automatically, and offer deeper integration with the respective cloud ecosystems, making them a default choice for virtually all greenfield projects. And yeah, I have been talking about L4 and L7. Let me tell you about what they actually are. To truly design a scalable system, you must understand the distinction between L4 and L7. L4 is simple, fast, and looks at only the basic IP and port information. It's unaware of the content of the request. L7 is where the modern application delivery happens. This load balancer acts as a reverse proxy, fully terminating the connection so it can read the entire HTTP request. This allows for powerful features like context-based switching, where you can send requests for your user API to one set of servers and request for static images to another, all from the same public endpoint. Furthermore, by handling SSL termination, the load balancer offloads the CPU-intensive task from your backend servers, allowing them to focus entirely on application logic. This fundamental difference is the basis for architecting highly specialized and performant microservice infrastructures. And that's the wrap. Load balancing might seem complex, but remember, it's all about picking the right algorithm for your specific needs and understanding when to use L4 versus L7. Real systems like Netflix show us that the magic happens when you combine multiple strategies intelligently. Load balancing isn't just a technical necessity, it's what lets your application grow, survive failures, and serve users worldwide. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.